I think the recording has started, so I will start. So what are like Diophantine equations are like an important concept in like number theory. So if you see a normal equations in like what are Diophantine equations if we ask this question? So normally if we have like some equations and if you have to solve them, you have like n equations and n variables. But here that's not the point. Here you will have like more variables and less equations to work with. Generally like 3 variables with 1 equation and stuff, but you will have the additional condition that stuff are integer, rational, prime numbers that will be given in the question. So now, if we think of like a random Diophantine equation, let's say, I don't know, I'm just making up something. Like this one where like x and y belongs to like a natural number or non-negative integers, whatever. So you will have a couple of different approach to go about it. There are like two main approaches. One are like modular contradiction and one is like size contradiction. There are also other approaches which I will discuss at the end of the class. So in modular contradiction, you want to show that one of the side is divisible by some number, but the other side is not divisible by that number. So they can't never be equal. And size contradiction is like if you like for large enough x and y, one side is becoming huge and the other side is like, if I want to say in like vague idea, another side is like small compared to that. This not might be only in the case of the all number, maybe some prime number which is dividing it, the powers of prime, that can also be like large and small. We'll more discuss about that. So the main way to like, if you have a Diophantine equation, how can you like differentiate between that it's modular contradiction you have to show or like size contradiction? It's like not a easy thing to spot. Like if you see a question, you can't like say in like 1 second that it's like modular contradiction or size stuff. So today we'll be doing like questions and we'll try to explore ideas that how to approach such a question. And I will not be revealing it's like in which part of this is. So normally if you like or when you are doing a class, you know it's like based on some topic. But today's class, like you have to find the idea. So this is the first question. You guys should give it a try. If you are done, uh, you can write me in chat also or tell in loud. So you have given it like positive integers x and y, and you need to figure out like when x square minus y factorial is 2001. Do you see any like obvious x and y pair which directly satisfies this? Anyone? Also, if you guys can turn your camera on, that will be great. Two thousand one, say it's like divisible by 3 at first. So yes, someone mentioned it's 45 and 4. Yes. So like 45 square is 2025 this year. So you guys should remember it. So 45, 4 is like a direct solution for this. But is there any other pair which satisfies? Is the big question. Like can for large values of y, can this equation be satisfied?
No, y must be less than 6 or 1, 2, 3 or 1, 2, 3.
Why y must be less than equal to 6?
Because if y is greater than equal to 6, so it's divisible by 9, and x also must be divisible by 3 if y is greater than equal to 3, because we have 2, 0, 0, 1, which is divisible by 3, but it's not divisible by 9, so we get a contradiction.
Yes. There is another way to also see the contradiction, that say y is greater than equal to 7. So it's like a thing with factorials. If you see any factorial is factorial. So if you make x large enough, you can use any modulo prime p, and you can make p divides x for x greater than equal to p. So you have some others one side and some other side. The thing is that you can make this number divisible by p, and if the other two sides doesn't like have the same like residue when dividing by p, then we will have contradiction. So if you see factorials, it's a good way to notify that maybe for some large enough cases, you can show modular contradiction. And so here, if you see like 9 also works, 7 works, a lot of things works, but just for the simplicity, I'm checking p equals to 7. By the way, can you guys see my what I'm writing here?
Yes, yeah, it's visible.
Nice. So if p equals to 7, then we have like for like y greater than equal to 7. 2001 is like 6 mod 7 if I'm not wrong. You guys can tell me if I'm wrong. And you will have like x square being minus 1 or 6 mod 7. But this is not possible because it isn't. Another way to see this is like, which we'll also like talk about next classes, that if minus 1 is like some square, it's called like a keyword, and keyword are only minus 1 is a keyword only if like this 7, like if this p is like a 4k plus 1 type of prime, but
I
7 is
think
like a 4k plus 3 of prime.
mod 9 also works because
Yeah, both mod 7 and mod 9 works.
yeah, because for 6 or more, n factorial is 0 mod 9 and a square can't be 3 mod 9.
Exactly. So I'll just scroll up. Now I was trying to wait. Yeah, I was trying to like see another thing. Try this problem. X square minus y factorial equals to 2024. Now which, like, it's like factorial and same kind of question. You have to think of modulo only. Which modulo you'll think of in this case? What is the most suitable number that you have to do like less cases to check and something like that?
3. 3
Three
mod
is
3.
So 2024, this is like 4, 2. This is 2 mod 3 minus 1 mod 3. And y factorial is like, for greater than equal to 3 is like 1, 0 mod 3. So x square equals to 2 mod 3, which is like direct contradiction.
Yeah, I mean mod 3 works then.
Yeah, mod 3 works.
Anyways, I have a good problem. May I share it?
Maybe after the problems that I do, you can share me on DM. I'll check that one.
I'm giving it in the chat. Or I have to tell it.
You can send in the chat.
Okay.
So if you have factorials, it's a good way to notify that probably there is some modular contradiction. Now, if we look at like something like x square minus 1 is equal to, I don't know, not x to not 2, let's say x to the power some power k is some like y to the power k1 is some power y to the power k2. So it may be there is like size contradiction, but the point is that say x square minus 1 is like a perfect square. Why can't this happen in most cases? Can you just say it quickly? Why x square minus 1 can't be perfect square in most cases? X greater than equal to 2. Anyone? Uh, like x square minus 1, why can't it be perfect square? Can you hear me?
Yes, yeah. I think it's because the spacing is generally not that much between squares.
Yes, so this is bounded, like this is less than x square, and in most times it will be greater than, not greater than equal to. For x greater than equal to 2, this will lie between two perfect squares. That's why it can't. It's also pretty natural idea. So see, if you have some kind of equation and you have like k1, k2, so what you want to do is try modular condition to prove that like this k1 is like kind of a multiple of k2. K1 is like some t times k2, and then use size contradiction on like is say that it will be between two power of k2s. Basically this function will lie between some a to the power k2 and some a plus 1 to the power k2. That's it can't be a perfect power of k2. This is a common way to show contradictions. Let's go to the next problem. Which one do you try? Let's try
P3
problem
looks
3
nice.
first. Yeah, let's try problem 3 first. I'll zoom in a bit. Yeah. So in P3, what do you want to do? You have the same type of thing in power and you want it to be some cube. So what type of contradictions are you thinking of in this case? For like large enough numbers. Oh, also one thing I forgot to mention in the first case, you should check for every value of y less than equal to 6 that it is a perfect square or not. So in this case, like so if it is greater than something, then you have contradiction and you check all the base cases. Sometimes these base cases also might not be too easy to calculate. So you also might have to show some contradictions in that case. We'll see a problem like that in later. You guys try this problem, I will some paste some new more problems. Okay, a derivative problem is a nice one, I think. I'll also do that. That's a nice one.
In the third problem, I guess you have to take mod 3 again.
Okay, mod 3. What does mod 3 give? Let's try mod 3. So M cube, what is M cube mod 3? Okay, like by
0 or
format
plus minus
3,
1.
yeah, it can be anything basically. So it's not that restrictive. The mod 3 on M cube is not that restrictive because it can be anything. So you don't get any information from that.
No,
So I
I
don't,
mean, any cube mod 3 is either 0 or 1 or minus 1.
yes, but like there are only 3 options and you get all 3. So do you get any benefit from that?
Yes, I guess there are no possible solutions to the equation given.
Can you explain a bit?
Like 11 is minus 1 mod 3.
11, yeah, this is -1 mod 3. 2 to the power n is also -1 mod 3 and 6 is 0 mod 3.
Yes, so 11 to the power of n plus 2 to the power of n is either 2 mod 3. No.
-1
get
mod
it.
3 is also 2 mod 3, right? So like if you get it to be some mod 3 also, then it won't help much and you actually don't get a fixed number in this case also in mod 3. So
Yeah, I
I
have to
don't think
take
mod
mod
3 is a
something.
good way to think.
Yeah.
Think of what, like in cubes, what does it give? Yes, Bhairav.
Maybe we should do mode 7 because then mode 11 and 2 become quadratic residues.
Exactly. I won't use the term quadratic residue, but mod 7 is a great idea to think. So in case you have like a cubes, it's a great way to think that mod 7 or mod 9 helps the most because x cube is like 0 or plus minus 1, mod 7 and 9. Because like 5 of 7 and 5 of 9 is 6, and so by like Euler thing you get a cube is 0 plus minus 1 mod 7 or mod 9. So you will get m cube as 0 or plus minus 1 mod 7. And what will you get on the other side? 11 to the power n plus 2 to the power n plus 6 mod 7. When it will be like 0 comma plus minus 1 mod 7. You want to check this. We can check each case, like you know that this function will be periodic after 6, basically modulo 7, because like 5 of 7 is 6. So if you n and do n plus 6, that will be like same. So you only want to check all n equals to 0, 1, 2, 3, 4, 5, 6. Yeah. You will get that this will only happen if you check modulo things when n equals to 3 or 6 mod 6, basically. The point is it is a QR, but I won't use the word QR because that means 3 divides n. So what I mentioned earlier, that you have some equation equals to some other thing and you want to show this power is like divisible by that power. So you showed that 3 divides n. Now what should be the approach? You know that I'm writing n equals to 3k plus 2 to the power 3k plus 6 is some m cube. Now what should you do? If you do you guys want buffer problems? I'll that paste it in the chat. You can write in
Sure.
chat.
Yeah.
Okay. Sure, I'll paste some buffer problems. You guys can't see my overlay screen if I am correct.
Yes. Yeah. We can't see that.
Now can't we directly do the size contradiction is greater than it's greater than obviously greater
Yeah,
than
so you want to show that this is like between two cubes. Which two numbers should you pick?
11 to the power of 3k and 12 to the power of 3k, and then just do something on k.
But 11 to the power 3k, 2 to the power 12 to the power 3k, I mean,
Yeah.
aren't there numbers, cube numbers between that? They are not like 11 to the power k and 12 to the power k are not like consecutive integers. So
3k.
Maybe
Yes.
11 to the k and 11 to the k plus 1.
yes, so this mq will just, this will be greater than 11 to the power k q, obviously, and you have 11 to the power k plus 1 q. So you want this number to be less than that number, and which should be in most cases. You can see 2 to the power 3k is like 8 to the power k, and in this will be like 11 to the power k only. So you will get like this. You can show this for everything. If you like open data 11 to the power 3k, like plus 3 into 11 to the power 2k plus 3 into 11 to the power k. So like 11 to the power k is itself bigger than this number because this is actually 8 to the power k. So this will hold for everything. So there is no solution to this equation. So basically what we did was we used a modular thing to show that n is divisible by something, and that something is perfectly chosen to be 3, because then we can use, because the powers are same, we can use this size thing. If you have something like x squared equals to y cube minus 1, it will be hard to show size contradiction because the both, my writings, my stylus skill is like pretty bad. So I'll write it once more. If you have x squared equals to y cube minus 1, it will be very hard to show a size contradiction in this case because the powers are different. Both of their growths are different. So you have to, like, this is by Catalan conjecture, which I mentioned in some time. Also, I think you can do it by elliptic curves, one of the methods that I won't discuss today. Okay, let's now do this problem. I have pasted the buffer problem. Those who want to try the buffer problem can try it. It might be a bit hard, by the way. Like, for anyone new, you should try these problems first. You have PQ prime numbers. In the like first two questions, we did with integers, but here we want prime numbers. So what are like special properties of primes? That
Maybe we could try mod 6.
mod 6. Okay,
Like,
sure. So let's say PQ are not equals to 2 and 3 because
We could do some
Uh,
divisibility stuff like p divides to q plus 3 and
yeah,
q
if P
divides
not
to
equals
square.
to Q, we can say to P divides to Q plus 3.
Yes.
By the
And if
way,
it is, then we can solve very easily if p is q.
should I change the thickness, or is it too like bold, my writing? I should change my thickness. Or is it fine?
We should change the thickness.
It's fine.
So do you think which idea should be good? Modulo, like taking mod 6 or something? Or this divisibility idea, and probably you will do something with this divisibility idea. Which one you think should be a good way to proceed?
Divisibility.
I agree.
Okay.
Divisibility.
divisibility.
Nice.
So let's try the divisibility idea only. If P not equals to Q, okay, let's try with P equals to Q. What will P equals to Q give? this will be just q square minus q minus 1 being
It will
2q
give
plus
P
3.
equal to, it will give P is equal to 3, I think.
What?
It will give equal to
The-
2, right? Q equal to 2. We just have to
It will
solve
give you
the,
no solution. I mean,
we just have to solve the quadratic.
minus 4 is equal to 0, right? If I'm not mistaken. And this has no solution. Like the
Wait.
solution is like q equals to 4, which is not a prime.
Non-prime.
Ah, yeah, okay, that makes sense.
So you know now that p divides to q plus 3. So what do you do with this info now?
We have sort of a bound on P, and then like Q also divides P squared minus P minus 1.
Okay, let's also write it down. Q also divides p square minus p plus 1. Yeah,
Minus 1, right?
okay, yes,
Uh,
minus.
Now we can actually take that P. Wait, sorry. Sorry, nothing.
No,
If we let like 2Q plus 3 is equal to KP, then like we can,
okay, do you want to write 2q plus 3 as kp? Sure. Or k is an integer. I'll mention that.
yeah.
Okay.
And then like you get Q is equal to KP minus 3 divided by 2.
I mean, do you want to use the divisibility condition or do you want to use the actual equality condition? You have a stronger condition. So do you want to put on a weaker condition this bound or do you want to put it on a strong condition?
We should put a stronger condition, right? Because
Yes.
then,
So
yeah, then
if we
P
put
squared,
in the
yeah.
equality condition, if we need the divisibility also, we can figure it out in the like from the strong condition.
Then
So
KQ is equal to P squared minus P minus 1, right?
I will write the equation. Right. Let me just see the equation. Okay, so we'll have p into p square minus p into p square minus 1 equals to like pk minus 3. Q is like pk minus 3 by 2 into pk. Remove this pp.
And you
Now,
can like multiply by 2, you can get kp minus 3 divides 2p square minus 2p minus 2.
sure, we want to use like divisibility condition, but will that help much? Like this is an equation with p and k. Do you want to make a quadratic equation out of this while like roots are integer?
Hmm.
Because this will be like kind of a nice quadratic equation to make. So let's write a quadratic equation down. I mean, not a quadratic equation, but sure. You can simplify it. I am not doing anything more. I'm just writing it down. Sure. Now you have P and K here in this equation. What do you want to do with this equation? If a like equation has like yes, looking at the discriminant. Looking at discriminant is helpful because like you have d is equal to like b square minus 4ac. So if the growth of ac is like linear and b is also linear, so that is a square itself. And you want this thing to be a like square number. So you'll probably can do some kind of size contradiction when you are looking at a discriminant of a quadratic equation. We don't know it for sure if it is like if it will be true here, but Why not try it? Like, so it will be k square plus 2 whole square minus 8 into 3k minus 2. Can this be a whole square? Because it has integer root. You want this to be like some t square. Can this be whole square in every case? Or will it fail somewhere due to some other condition?
Uh, I mean the degree is even, right? So some bounding should work.
Exactly. So you have this k square plus 2. You know that this is less than k square plus 2. So you know that t should be less than k square plus 2. If you can show that t is greater than k square plus 1, then this can't be a perfect square. Like this idea is pretty common that you have some number, if it is a whole square, this will lie between two perfect square. Not only squares, for any perfect m power, you can show that this quantity lies between two perfect m powers. So what is k square plus 1 whole square? K to the power 4 plus 2k square plus 1. And you want this to be like this thing to be bigger. K to the power 4 plus
4k squared plus 4 and then minus that thing.
4k square minus 24k plus 4 plus 4 minus not plus 60, if I'm doing the calculations correctly. Right. And this is like
Yeah.
and this is like k squared. So and this is 2k squared. So if you like make k large enough, even if this is 24k, this won't affect much because the coefficient of higher degree term is more. So you should be able to do size contradiction. In this case, if you, I think for k greater than equal to 11, this is 2. So you have to manually check k equals to 1 to 10. And this is a homework for you to check k equals to 1 to 10. I'm not going to do it here. I'm just telling what's the solution. For k equals to 5, you will get that p equals to 30 and q equals to 31, which is the only solution. Any issue with the problem? If any issue with any of the problems till now, like those 3 problems, you can write in chat or tell me directly.
I was wondering like what would be difficulty of this problem? Like, is this feasible for RMO or something like that?
This should be, I mean, this is not, I won't say this is easy RMO question, but this can come in RMO. Actually, this is the TST question. This is Croatia TST P4. But I mean, it's nowhere near TST difficulty if you see in other countries, but sure.
Okay.
Okay, there is like, I think there is no issue with anyone. I didn't see anything in chat, so we'll move on. So, do you want to do more problems or discuss some other ideas like infinite descent? Or we can do more problems in this also.
Can you give some more
Oh.
problems?
Sure.
Because like infinite descent is not that hard.
Yeah, I'll discuss that. Let's do this. You have done the previous classes, right, of orders and VP stuff. So let's try this problem. I'll explain another. Uh, Try this problem till now. I'll paste another problem. This is more becoming like a NTPSS. Right. Did it change both the problems? What happened? I'll paste the first problem again. Okay. Try this problem first. If you're done with this, then try problem 4. There is some theorem which directly kills it. I will also
Zsigmondy, right?
discuss that in a way. Zsigmondy, yes. But try without Zsigmondy for now. I mean, in RMO, you can't really use Zsigmondy. The point is knowing theorems like Zsigmondy and RMO helps because you know that what is the answer. Even if you can't use it, you know it is what is the answer.
No, I mean, they can't. I mean, if I do the problem correct using Zsigmondy's, can they cut my solution?
In RMO, yes, because you are not proving Zsigmondy. And if you prove Zsigmondy, you can't write any other.
It's because some of the graders don't know Zsigmondy. Not all
Most
of
traders
them
don't know Zsigmondy. I mean,
knows.
only Mumbai or Delhi might be fine. Like, don't try it with other states.
And in general, even if they do know, they may not want to give points since they want to see your if you can do elementary solution.
Because it's coming in RMO, you know that there is elementary solution. They won't give a Zsigmondy problem in RMO.
Yeah, that's true. But like
So
generating functions, like I use generating functions.
functions can be used. Zsigmondy is like something like it's a theorem which has like not so easy proof. So if you want to prove this, like they also might ask to prove then like prove Zsigmondy, which you can't do in
Like
like 3
if
hours.
I give a solution using Fermat's last theorem, I have to give the proof to Fermat's last theorem too.
Yes.
Yes, and you can't give. So don't use Fermat's last theorem in RMO.
I
State
mean,
advice.
yeah. Thank you.
We could do this with VP bounding.
Okay. Can you
V3
tell?
of V3 of tutor n will only be roughly log of n, and same for V5 and V7, meaning that for sufficiently large n, the size of the VPs becomes too small, and then for the remaining smaller n become k sparse.
I see the idea. I didn't do this, but I see the idea.
Wait,
There is
what
the
is the idea?
easiest. He's taking VP of 2 to the power n minus 1 and seeing like the number of primes dividing it. And it's like roughly log n, I think, if you are saying correctly, right?
Yes, at most roughly log n by. I think we can even do better than that if we try.
I think it's, but proving that it's roughly log n by n is not trivial at all. I don't think.
Like this is kind of the density idea, but we will not go into this idea right now. Like this, they're like normal solutions, which are like not too different. Let me check the source of this problem. Okay. So any ideas? How can you show that? Like you have 2 to the power n minus 1. What is 2 to the power n minus 1? What is good about it?
Sums of
See,
powers of 2.
uh,
Not
I
exactly
mean
useful.
that is more useful in combi 2 to the power n minus
Yeah.
1 than nt. If you have like some prime dividing n, what will you have in this case?
Then
What
it
does that
can't
imply?
divide 2 to the power n minus 1. Well,
Oh,
n cannot divide 2 to the
can
power n
you
minus
say
1.
again? I can't hear you.
Like if we take the smallest prime divisor of n, then it can't divide 2 to the power n minus 1.
No, I'm saying for any prime divisor of n, what will that imply that what will divide 2 to the power n minus 1?
Like the order of 2 divides n, like that, or
I mean, you will have 2 to the power p minus 1 dividing 2 to the power n minus 1, basically. Right? For some prime
oh,
which
acha, prime divides n. Oh, okay.
Does everybody see why this is true? If you have a prime number dividing n, can anybody want to explain this, why this is true?
Because
Someone?
like we can write
Yeah.
n is equal to pk, and then like 2 to the p minus 2 to the n minus 1 is just 2 to the p whole to the k minus 1. This of the form a to the p
Exactly.
minus 1 divided by
I'll write that one out. So 2 to the power p is like 1 mod 2 to the power p minus 1. If you do k here, say pk is n, I'm not writing. This will also be 1. So this is 2 to the power n is 1 mod 2 to the power p minus 1. So 2 to the power n minus 1 be divisible by 2 to the power p minus 1. Can you use this fact to do this? Try to using this fact. Also, this might use orders in some places. I'm just saying it out loud. Yeah. So you have any prime that divides in 2 to the power p
so
minus
p
1
greater
divides.
than okay, can we say p greater than 7 cannot divide n? Like if we can do some induction stuff, right?
Exactly. So the point, not induction, I mean, wait. So there is one claim that I'm trying to prove. This is helpful in general, not only for this problem, that the largest prime divisor of 2 to the power n minus 1 is like what should I say? It's like more than the largest prime divisor of n, basically. Do you see why? Like strictly greater than, say, the largest prime divisor of 2 to the power n minus 1 is some, I don't know, a, and largest prime divisor of n is b. So you'll have a greater than b. Try to prove why this is true.
Sorry, what's the definition of B again?
B is the largest prime divisor of n, the number n.
Okay, and A is equal to the n minus 1.
Yeah,
Yeah,
largest
for
prime
this
divisor
we
of
can induct, right? I think like suppose this statement is true for like till m, and then like you take m plus 1. So like take the largest divisor of prime divisor of n plus 1. Like you will have the by the induction hypothesis, you will have that the largest prime divisor of like if q is the largest prime divisor of 2 to of m plus 1, then like 2 to the power q minus 1 has a prime divisor which is greater than q, and like this thing also divides 2 to the n minus 1, so we should be n plus 1 minus 1.
Yeah. There is another proof using orders, which I will do. So take a prime. I see you proved the Riddhiman. That's correct, I feel. You have key device 2 to the power p minus 1. So what is the order of, I should write q here.
Is p only.
Why isn't it? It divides p, but why is it p only, not 1? Because
Because it cannot divide 1, right? 2 minus 1.
yes.
Yeah,
So it's
that
p.
is why 2 to the n minus 1 is good.
Yeah. So ordered is like order divides like q minus 1. So p divides q minus 1, basically. So that implies that q should be greater than p, which proves this. If you take the largest prime divisor and largest prime divisor in this side, we will have Q greater than P. That means like A greater than B. So now know that if n is some like Q1 to the power alpha 1 like this, the prime divisor can't be like 7, 11, those type of things, because then the largest prime divisor of 2 to the n minus 1 also have like prime divisors more than it. So basically, n is composed of only 2 primes, or not 2 primes, right? Like 2 to the power n to 3 to the power b into 5 to the power c.
I don't exactly see why should n have only those many prime factors.
Because if n has 7 as a prime divisor, then 2 to the power n minus 1 will also have like a prime factor which is more than 7, which can't be followed because of this equation.
Right. Okay. Okay. Right.
Now, why can't now you have like 3 prime divisors. Try to do something on this.
Okay. Wait, this ABC is different from the ABC in the question, is it? Right.
Yes, say A dash, B dash, C dash.
What if we use like LT to get something about V3 of 2 to the power n minus 1?
Don't go into LT stuff. I mean, you know that for any prime divisor n, like you have this. So if you can make like this number another prime number, which is like not 3, 5, 7, you will be done basically, right? So basically, if 5 divides n, you will directly get that 2 to the power 5 minus 1 divides 2 to the power n minus 1, which means 31 divides 2 to the power n minus 1, which is directly false.
So it can't even have 5. So it has only
Yes.
2 and 3.
2
That's
and 3.
not
Now,
right.
use this idea to show that our price of 2 and 3 can't work. Like,
9 can't work, right? 3 squared can't work.
yes, if b dash is greater than equal to 2, this can't work, because then like 2 to the power 9 minus 1 will divide this thing. And 2 to the power 9 minus 1 is like 5, 11. What's the time factorization of it?
7 divides it, right?
Okay, 73 into 7. So 73 divides it. So this also can't work. So you know that b dash is either 0 or 1.
And A dash is like 0, 1, 2, 3 because like 2 to the power 4. Okay, no, it can't
2 to the power
be.
8 minus 1 also can't work. See, because 255. And if we divide by 5, it's like 51. And 3, so
Yeah.
17 basically. 17 divides it. And because 17 divides it, then A dash has to be like
0, 1 or 2.
0, 1 or 2. So you will have options. You will get the number like 1, 2, 3, 4, 6, 12. And only 12 doesn't work here. If you check it explicitly, 12 doesn't work. All the other 5 works. So answer is 1, 2, 3, 4, 6. And now I'll show another idea which directly kills the problem, but you should not use that in Animo. I think using Zsigmondy and Inmo is fine, but don't use in Animo. So if you have a to the power n minus 1, you can also do it plus 1 by same method, which I'm not doing it. Then what can we say in Zsigmondy is a is a fixed number and you are increasing n. So there will exist a prime such that p divides a to the power n minus 1 such that p doesn't divide a to the power k minus 1 for all k less than n, except some exceptions. Obviously, a equals to 1 is an exception. N equals to 2 is, I think, an exception. N equals to 2 and whole square, basically. And another exception, which is like a equals to 2, n equals to 6. So 2 to the power 6 minus 1. This is like 63. So it has 7 and 9, 7 and 3 as prime divisor, but 2 cube already, minus 1 already has 7 and stuff. So these are all the exceptions. For everything else, a and n, you will get a new prime divisor. So in this problem, basically 2 to the power n minus 1 for n greater than 6, because 2 to the power 4 minus 1 already had 5 as prime divisor, and 3 and 7 is like in 2 to the power 6 minus 1. For any n greater than 6, this will have a new prime divisor, which is not like 3, 5, and 7. That's why this can't work directly by Zsigmondy. So you only need to check from n equals to 1 to 6, and 5 doesn't work, only other 4 works. This is also a motivation that why 2 to the power 12 minus 1 doesn't work in this case. Like, if you don't want to check, you might feel like everything works, that like we did this, so everything should work, but actually 12 doesn't work in this case. And Zsigmondy is a good motivation why 12 doesn't work. Now do this problem. After this, we will discuss infinite descent ideas. If we have time, then we can discuss Vieta jumping, or we can discuss Pythagorean triplets. One of the two things. By the way, for this problem, the source is a Korean something, Korean name. I haven't read. Yeah, 2 to the power n plus 3 is prime. Why 2 to the power 2n plus, not 2 to the power n, 2n plus 3 is prime? What is that? Is true. Somebody wrote in chat, I think. Can you tell why this is a prime?
Because like all like the numbers 1 to n does not divide n factorial minus 1, and like 2n plus 3 has to have a prime divisor from 1 to n.
If it is not a prime.
Yeah, if it is not a prime.
Exactly. So this is a prime. What can you do more? So divisibility with prime is good, right? Because you can use a lot of things in primes. So how can you use that?
So like we can rewrite, right? N is p is equal, like n is equal to p minus 3 divided by 2. So you have p minus 3 by 2, the whole factorial is congruent to 1.
But like you have p minus 3 by 2 factorial. Is it a nice number, like by 2 factorial? Like, do you
Yes,
want to rewrite in p terms, or
we should rewrite in p terms because okay, like Wilson's, like we have to bring it of the form of Wilson's theorem somehow.
exactly? You have factorials and divisor stuff. You have to use Wilson's. But how to use Wilson's is the point.
So if we make it like if we multiply by p minus 1, and then we will get p minus 1 by 2 factorial, and then if we square, I think we will get p minus 1 factorial. Well, actually no, we have to be a bit careful, but I think the general idea is that.
Anyone else, any idea? I'll just grab my water bottle for once. Yes, any more ideas?
We try to use Wilson's theorem, and we have
Pardon,
p
that's
minus
not
2.
true. I mean, I don't think that's true.
Wait, no, right? No, wait.
Yes,
One thing.
by what's your idea?
Yeah, like how will you remove the by 2?
We can't. Like we can. I mean, by 2 is not a good way to write. You should write in the terms of 2n plus 3 only. Like both the things are isomorphic, so they are fine, but it looks a bit ugly. P minus 3 by 2 factorial. What do you know in Wilson? We can yes, Ronit?
Yeah, no, you were saying something like you should rather use the 2n plus 3 form. What do you mean by that? Like instead of using p, use n? But then how
Yes,
will you
we use n only. Like we write the equations in n term because of this by 2, it might get a little messy than how to take numbers and stuff. So 2n plus 3 like feels like good. Like both obviously works because you're essentially doing the same thing, but this looks a bit nicer than this one. Opinions might vary. So
Well, we have that p minus 2 factorial is congruent to p minus 3 by 2 factorial, not p,
yeah.
by
What,
itself.
what I mean is we try and use half of Wilson or something, because p minus 1 by
Yeah.
2
So what you
factorial.
want to do is basically that exactly the idea. You can write like some p minus 1 stuff as like a minus 1, right? A p minus 1, 2 by like minus 2, and you multiply, and that becomes like the first 1, 2, like their whole square basically. And only this minus term will be there if you write in that way. Exactly. So I'll just write that idea in like in terms because. So you know what you know is 2n plus 2 is like a factorial, obviously. Minus 1 mod in fact mod p. P is like 2n plus 3. You know that n factorial is 1 mod p. So you remove the n factorial stuff. You write like 2n, not n plus 1 into n plus 2. What you can write n plus 3 is like minus n, like 2n plus 3, like n plus 3 minus 2n minus 3. So that just becomes like minus n, then minus n plus 1, something like that. So what it becomes when you multiply is minus 1 to the power n, all the minuses are n times, into n factorial, which you already know is 1. So you want this to be 1 mod p. So basically you get is n plus 1 into n plus 2 is plus minus 1 mod 3 depending upon the parity of n. Is this a contradiction? So if n is even, n being even, what we get is, let me just zoom out a little bit. For n being even, what we get is n plus 1 into n plus 2. This is like 1 mod 2n plus 3. For even this is. For odd, the same thing should be minus 1 mod 2n plus 3. Now, when can this hold? Like now it's like not hard. You should be able to finish. If you just expand it, you
Equal
will
to,
get
right?
like,
For
yeah.
simple, for ease of calculation. Otherwise, we have to like expand the quadratic and do some stuff.
It's like only 2 terms. You don't have to do any stuff, but like 2n plus 3 is prime. So basically what you have is like n square plus 3n plus 2 minus 1. So one sec. N square plus 3n
Plus 1, right?
plus 2 plus 1, yeah,
1. Yeah.
is 0 mod 2n plus 3. And now there is like,
We can multiply by 2 and like we can remove the 2n squared term.
yeah, like that is perfectly fine. Like this is the size bounded from here, but what you can also do is like like both are like same difficulty, like nothing, like everything is easy from here. You will get just subtract 2n plus 3 because you will get like n square plus n being 0 mod 2n plus 3. So n into n plus 1 being 0 mod 2n plus 3. But 2n plus 3 is the prime itself. So like it has to divide one of them, but this is bigger than both the things. So it can't divide one of them. That is false. And from here you will get like 2n plus 3 divides n minus 1 or n plus 2. So for only n equals to 1, this satisfies. Otherwise, this should be greater than everything. And only 0 can occur here when n equals to 1. So the only solution of the equation is n equals to 1. Okay. Any problems with these two problems? Any issues with these two? I will check the chat quick.
How did you get n plus 1 times n plus 2 and
Can you repeat what did you say, Tanishka?
how did you get n plus 1 times n plus 2?
Yes, I'm telling. Let me zoom in a bit. Why can't I zoom? But what happened with my mirror? The point is like, if we do 2n plus 2 factorial, what it is like n factorial, like 1 into 2 into 2n plus 2. So it's like the first n terms, if you take, that's n factorial. Then you like make n plus 1, n plus 2 as like themselves, don't touch them, and take 2n plus 3, that term, as like minus n mod 2n plus 3. 2n plus 4 as minus n plus 1 mod 2n plus 3. So that just becomes n factorial from reverse with a minus sign. And it's like n terms, so it just becomes minus 1 to the power n into n factorial. So because we already know n factorial is 1 mod 3 from the given condition, so you can just cut this in 1 and do casework on the other two. Do you see it now?
Yeah, thanks.
Okay. So now should we do infinite descent? I have some more problems we can do, but let's touch infinite descent.
Can you just
Okay.
give the problems in the chat?
I will send to the whole thing after the class.
Okay.
Send the whole PDF after the class.
Okay.
So infinite descent is the idea that you have something. It's not only used in like NT. There are some common problems I have seen where you can use infinite descent idea. You have something, you consider there is some pair A comma A1 comma dot 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 AK which works as the given solution. From there, you show that there is another pair b1 dot 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 bk, which is a solution. But the point is, this can't always happen if you take this solution to be the minimal solution. This minimal idea is vague, but you can take it in quite a different ways. One of the most popular ways is taking summation of AIs to be minimal. And if you show that there exists a solution, summation of VIs, which is less than summation of AI, then your assumption is wrong. So you have a contradiction. So this is the main idea of infinite descent. It's not as hard as I said here, because mainly if you have equation, what you want to do is if some A comma B pair works, you want to show that A by some K comma B by some K also works. And then we will have infinite descent. That's basically idea in the Diophantine equations. So I will just paste a problem to demonstrate the idea.
Also, can't we show that an equation has infinitely many solutions?
Yes, from there we will have infinitely many solutions. Which are
From a pair A comma B, we might get a pair B comma some A1, which is greater than the pair A comma B, and so on.
yes, but there might lie infinitely many solutions. So if you take to be like there might not be such thing called a maximal pair, but if you have positive integers to work with, you must have something called minimal pair. That is the point of infinite descent. You can bound on the lower thing, but you can't bound on upper thing. So if you
No.
show there is infinitely many, so there isn't anything you gain from that.
Even
I
if we
mean,
do show infinitely many, it all lies on the assumption that the first solution exists, right?
Yeah.
Yeah. I mean, you are trying to prove that there is no solution except the trivial 0, 0 in some cases.
I
That
mean,
is
it
the
depends on
solution.
the problem type. If the problem type says
Yeah,
to,
yeah.
so I have done some of that problems in Aditya Khurmi.
You mean in Mont?
Yeah.
Yeah. This problem is not in Mont, so this is a easy problem. You can try it. It's not too hard if you have seen the idea before what to do.
Okay, we can do using modular stuff as well, right?
You have to infinite descent is an idea. It's not something that you have to use modular things to show that if A comma B pair works, then A by P comma B by P also works.
But even except for that, x squared plus y squared is 0 mod 3, then x squared is minus y squared.
These are in rationals basically.
But rationals also exist in F3 or FP, right?
Yeah, it does.
So we have something squared is congruent to -1 mod 3, which is a contradiction. Does that work?
That does work. I didn't think of that.
But the only issue I see is if the numerator is divisible by 3, that is only what I was
Yes, you have to also show here both the things will be 0 mod 3 then.
and that is where
And that is the infinite descent idea, basically. So I'll explain his idea in another sense. Write x as some A by C, y is some B by C. If the denominators are different, you can multiply numerator and denominator to make it same. So you will get a square plus b square equals to 3c square. But ABC are integers. Most of the time integers are better to work with. Now his idea was this is 0 mod 3, right? We know that square is 0, 1 mod 3. So if you have this 0, 1 mod 3, this is also 0, 1 mod 3. This can only be 0 mod 3 if both the things are 0 mod 3. So that means 3 divides A, 3 divides B. But that also means that as 3 divides a, 9 should divide a square because 3 is the prime. And 9 should also divide b square. And if you like write 3 here, cancel it out, you get 3 also divides c square. That means 3 divides c. See, you essentially have every ABC is divisible by 3. So if a comma b comma c is a solution, then a by 3, b by 3, c by 3 is also a solution. You can generate a solution from a solution. And you can take a plus b plus c to be the minimal pair, but this violates that. So you are done. Do you see the infinite descent idea? Anyone with any issue?
Yes, we see the idea.
Someone gave a problem in chat. I can take that out. Like a1 to the power 11. I'll just write in summation. You don't need positive integers. I don't think you need positive.
No, it is positive integers. I mean, the problem statement gives you that.
Yeah, but you don't need that. I'll do it integers.
Okay.
And you have like ei to be integer. Like for positive integer, it's quite obvious that
Size, right?
yes, like if like all thing has to be 1 to be like if you don't want to exceed, but all 1 doesn't work. So ei being integer, that is where it is.
I mean, my idea was to take mod 23.
Yes.
Yeah, it was similar to the one that came in stems, right? But for like from J1 to 10.
Yeah, it was like 2020, like A1 to
2057, yeah.
A11, 2027 years, something like that. I don't exactly recall the problem. So here you take mod 23. Why did
Yeah.
you think of mod 23 at first?
I mean, Fermat's
What's
little
the
theorem. And
yes?
that,
So
2
the
into
point
11
is
plus 1.
a to the power 22 is 1 mod 23 for every a.
and that like says that a to the power of 11 is equivalent to plus minus 1 mod 23.
0 plus minus 1.
Yeah, if you take integers.
If we take divisible by 23. So if you have 0 plus minus 1 mod 23, but the point is like if you have 0 plus minus 1, then all of them are 1 or minus 1. There'll also be like 5 mod 23 or minus 5 mod 23. They can't never be 11 mod 23. And this is not only for
Yeah.
11. You can do it for even 6.
Yeah.
You can do it 6 idea. Because this will max be 5 mod 23. So every number has to be divisible by like 23, 0 mod 23. That makes it like that can't happen. So that's just a thing. Okay. Now there's 2 choices. There is not much time. We can do Pythagorean triplets or we can do Vieta jumping.
Vieta jumping for today, if you want.
Yeah, you can write in chat. I will see the chat. I can max to only one problem, I feel. Vieta. Others, can you? Everybody is Vieta, so I'll do Vieta. I won't do the famous problem. I'm on 1988 P6. If you guys haven't tried that, I'm writing that problem.
I mean, that has gotten at the point of a routine problem nowadays.
Exactly, that's why I'm not doing that. I must have done the problem more than 10 times. If you haven't done this, solve it after the class. Like, I'm just boxing this out. This is kind of like the birthplace of beta jumping.
Yeah.
I'll do another problem. I mean, Vieta jumping, the idea is hard to describe if you not do a problem. Essentially, what you do is like the same idea as infinite descent, but you do that with the roots of a quadratic equation, and you jump from one root to another root. Like if x is a solution, a comma b is a solution, you show that if a quadratic equation has a as a root, that will also have like x as a root, or x is like less than like, and you show that by like some size or something, x is less than a. And the point is, if you take a plus b to be minimal pair, then x comma b also satisfies, and that is the minimal pair. So that violates the thing. That's the main idea. If you guys didn't understand, then like the problem should make that clear. If xy divides x square plus y square plus 1, then x square plus y square plus 1 is 3xy.
It's again a classic.
Try this. Have you seen this problem before? I have another problem. If you
Mon,
guys have. Like that was a buffer problem in Vieta. I can give that. Anyone finish with the buffer problem? I have another buffers if you guys want.
Wait, I don't think I have the buffer problem. Can you just show it once?
I pasted the chat, I think.
Oh, I joined after that.
Yeah, I'll
Cannot
paste
see
that
the
again.
previous chats.
I'll paste that again. No worries. Okay, I'm pasting here only. Take a screenshot.
Okay.
Yeah, take a screenshot of this. Also, if anyone are done with the, I'll post another buffer problem. Those who have done this Vieta question, I have another Vieta question. They can try that one. I think I have only one. I have time for only one question today in Vedas. I'll paste both the things side by side. Try the question 10th. If you have done this one, I explain this one in a bit. Though those who haven't tried this before should try it. And if you have progress for any 10 or problem like these two problems, you can DM me over Discord. Even after the class you are done, you can DM me over Discord.
what's your user ID?
Crystal Mind, you can see.
Sorry, I was being dumb.
If you're done with the first buffer, try this problem. If you're done with the problem 13, try the problem 10. Any ideas for this problem? Anybody who is trying it?
Problem 10.
I know this problem, like I will be discuss. This is like buffer problem, this too. I won't discuss this in the class. If you solve this, send me over Discord.
Okay.
We can make a quadratic equation in like x or y is symmetric.
We can, but will that help? We need to like we need this number basically, x square plus y square plus 1 by x y equals to, say this is k.
Then like
We need to get what is k. Should we include the number k in our like quadratic equations?
yeah, we should, otherwise
Yeah,
we
and
won't
then
get
we can get some kind of size contradiction.
we can get stuff about its roots.
Also, like I'm very inclined to do minus 2x. If that means then
Wait, completing the square.
yeah.
How do you want to complete the square?
Like EDN, the subtract or add 2x. So you get if it
Okay, like you mean x square plus 2x.
yeah, or x minus y or something.
Yeah, so that will make like x plus y whole square plus 1. Yeah, that's not a bad idea. That's not a part of my solution though, but yes, I can see that idea. Like that shouldn't matter too much. I mean, you can do x plus y whole square plus 1, and then the answer will be like 5 here without not 3. So like you have to do this idea, like that won't change the problem. Like you can modify a little bit, but the main idea wouldn't change. Let's take now the idea of ours for Vieta jumping, a comma b to the minimal pair which satisfies for k. Minimal pair. So we can also tell that to be k, ak, bk. I will be writing a and b everywhere because writing ak, bk is too much work. So write ak to the minimal pair which gives k. So, I should have mentioned catalog, but I'll do this first and then mention the catalog. What, like if you write this in a quadratic equation, you will get like some z square, like where z is a basically. I'm not writing a because of, you will see why I'm not writing it. A b z plus b square plus 1 equals to 0. Okay, and one of the roots is a here, like as the equation, like that's who we got one root to be a. What is the other root is the question. We say the other root is c. Okay, so this is the whole point. If see that if a comma c is a comma b is a solution, which is the minimal, c comma b also has to be a solution, because like we can get from here, we can get here, and that gives the same k. So that's the whole point. If a is the root and solution, the other root should also be solution. And now what is this other root? From Vieta's equations in quadratic equation, so you get c plus a to be like kb, so c is equal to kb minus a. I'll just and ac to be b square plus 1. What is the first? See, k is the integer, b is the integer, so this is the integer. You're subtracting an integer, so that will be integer. So c belongs to z. Now a is a positive integer, b square plus 1 is also a positive integer. So c is like positive, so c has to be greater than 0. So we get c also belongs to n. Do you see both the ideas? First we did integer, then we did positive integer. And now the main idea is that because see, the equation is like changing a and b doesn't change. It's like x square plus y square plus 1 by xy. If we switch x and y, it doesn't change much. So what we can do is taking a greater than b, greater than equal to. And now c will be like b square plus 1 by a. If A is strictly greater than B, then C will be strictly less than A, which is false by our Vieta thing, because we took this to be the minimal pair. The A plus B should be minimal, but here B plus C is minimal pair, which is false. So we have to get A equals to B. And if A equals to B, if we put that in the pair, we'll directly get that A equals to B equals to 1 has to be the minimal pair in for every K. Like this is the minimal pair. So this gives us K equals to 3 when we put A equals to B equals to 1 in the equation. This gives us 3 by 1, which gives us 3. So K has to be 3 in all cases. And there is one interesting thing that from A equals to 1, B equals to 1, you can generate like infinitely many solution. You can work backwards. So like you can do 1, 1. From here you can do like 1, 2. From here you can do like 2, 5, and you can generate solutions. You can make recurrences about the solutions. I'm not doing that right now. So this is the main idea of Vieta jumping. Try to this buffer problem. You can take a screenshot if you haven't taken before. Just you can try these 2 questions as like homework or something. I don't know. And I will mention just another thing. There is another conjecture which like don't use it in RMO. Like disclaimer. A to the power x minus b to the power y. If this is like 1, like if 2 perfect powers like x and y are distant by 1, then there is only one solution, which is like 3 square minus 2 cube is 1. There is no other solution. This is also called like Catalan conjecture or like Milkowski conjecture, I think. There are like some problems which we like the proof of this is like easier than proof. Like you can do the proof. It's not too hard like Fermat's last theorem. Still, it's quite a hard proof. I won't do it. The proof of Zsigmondy is also doable, but they're a little bit hard. I think we're at like almost ending. It's like 5:46. Any doubts or any more thing to say? Like I will end the class. Any doubt? You can.
have one thing, the infinite descent idea, like we can does it work for only positive integers? Like why do we need it to be positive? Can't we just have like an integer?
Not exactly. We can't work with any integer, right? Because x and y are positive in the question. So if you want to be another pair to be satisfied, I didn't write that. That was my mistake. Sorry. So you also like if you want C, B to be a valid solution pair, that has to be C has to be an integer, right? So you want that to be a positive integer only.
Okay.
Otherwise, it is not a valid solution pair. Like
And
what you're showing that if ever, yeah.
I was thinking if like C is not positive integer, then the idea ki C is less than A, it won't work, right? Because like you can get 1 and then after that 0 and then -1 and dot
Yeah,
dot.
yeah, that won't work if C is not
So
positive
if we
integer.
have negative integers, like if we just have integer, then we should discard this idea, or like how do we?
You
Is there
can,
a workaround?
if you have only negative integers, you can do like everything minus, and you can change the equation to be something to make it like positive, and then work with that. But if you have like both, you can work with both positive and negative. I don't think you can use this idea unless you prove something else that it has to be like everything has to be positive, everything has to be negative. I don't think you can directly use this idea when you have like x and y belongs to z, because the minimum solution idea is like doesn't work because it's not bounded from below nor above.
Oh, okay.
You might work with mod x plus y, but I actually haven't done any problem like this. You can try with this to be the minimal pair, but I'm not sure if how much easy it's to show this, because I don't think this will be too hard to show in most cases. if x comma y is a pair. Yeah. Any other question? Otherwise, I will end the recording now.
Yeah, I don't think so.
Yeah, I'll end the recording.